Hello, my name is Robert Smith and I'm with New River Community College's Academic Assistance, and today we're looking at equilibrium constants. These will show up quite frequently over the next several sections, so it's good to become familiarized with them. So let's get right to it. We're asked to write the expression for both our equilibrium constant of concentration and our equilibrium constant of pressure, if possible, for the following reactions. Now the thing to remember when you're doing this is that you're only going to include instances where the phase of the matter is either in the aqueous phase or in the gaseous phase. If it's in the gaseous phase, you can do the equilibrium constant of pressure, which is Kp. If it's only in the aqueous phase, you can do Kc instead, but you wouldn't be able to do Kp. Okay, so our first equation is hydrochloric acid plus water yields the hydronium ion and a chloride ion. And they're all aqueous except for water. So keeping that in mind, we can write Kc, and we would do products over reactants. That is the standard by which we address all concentrations and concentration constants, equilibrium constants, and so forth. So in this case, we're going to look at the concentration of chloride times the concentration of hydronium. And it's all over the concentration of hydrochloric acid. Again, note please that we did not include water because the phase of water, right here, is a liquid. Whenever you record the concentrations, you're only going to record the figure amount for the concentrations. Do not include the unit. It will not give you necessarily the correct unit if you include the units. Recall that equilibrium constants are unitless. So if you record the unit, then you're doing it wrong. The reason they're unitless is because whenever you record the concentration, let's say, if it's molar, it's related to whatever this molar is. It's always related back to 1 molar. So then your molars cancel out, your molarities cancel out, and you're left with just X, whatever that value is. And that's true in all cases of equilibrium constants and other similar devices that we use in chemistry. So always recall that you should never have a unit attached to your equilibrium constants. So that's all there is for the first one. Second one is given to us in gaseous form. So we have N2O5 and yields NO2 and O2. They're all in gases. So let's get Kp. And Kp is going to be products over reactants. So we've got, actually this would be a P, O2 times P NO2 to the 4th power all over and all over P of N2O5 to the 2nd power. Note the exponent matches the coefficient in front of the species. So over here we have 4 NO2s, so we raise the pressure of NO2 to the 4th power. Similarly, we could write Kc, although typically if you're only including gases, you'll only worry about Kp, but we can always do Kc as well. It would be O2, NO2, again to the 4th power, over N2O5 to the 2nd power. Okay? Our last one has a bunch of organic stuff. Don't worry about if you don't know the name of it, just worry about what the phase is. So we have an aqueous phase, we have a liquid phase, we have an aqueous phase and an aqueous phase. So the liquid phase we're not going to worry about, we're only going to worry about the aqueous phases. So we end up with this nasty compound, although it's actually quite useful in organic chemistry, but I won't confuse you with some of the terminology that's involved in it. That's for a later video. Once you start doing some of these, they become automatic. So it's really important, it's really important for you to just get used to putting down what the expression for the equilibrium constant is. Okay? So that's it, just products over reactants. And raise each reactant to, and each product to the power of its coefficient. So going to the next problem, we're given a reaction and we're told what temperature the experiment runs at, and we're also told what the concentration of the various species are at in equilibrium. And we're wanting to calculate what Kc is at that temperature. Recall that your equilibrium constants will change with temperature, so it's crucial to understand that as long as the experiment is run at the same temperature, you're going to get a specific K constant. If it's run at a different temperature, you will get a different K constant. So it's important for you to recognize that and work with that as you proceed. So for this one, we're going to just write the expression just like we did before. Kc is equal to the concentration of O2 gas times the concentration of NO2 gas to the fourth power, all over the concentration of N2O5 gas raised to the second power. It's the same expression that we had in the previous problem. Now it's just plug and chug. So using the values that are given in the question, we could just say 0.271 molar times 16.6 molar squared, edit. So we start with what's given in the line, 0.271 times 16.6 to the fourth power. Remember, you're leaving out the units. And in the denominator, we have 0.0452 squared. Then just plug it into the calculator, and you end up getting Kc is equal to 3.66 times 10 to the fourth. It's pretty simple. This illustrates how simple it is to calculate your K constant once you have your expression properly done. Okay? So the next problem, keep it rolling. The next problem gives us again a reaction and a temperature, and gives us the Kp value, as well as the partial pressures of some of the components. And what we want to do is find what the partial pressure of oxygen is in this reaction. So we have to set up our Kp expression. And again, we have nothing but gas, so we don't have to worry about changing and leaving things out. So in this case, we have the products are the partial pressure of NO2 squared over the partial pressure of nitrous oxide squared times the partial pressure of oxygen. Now, I always find it much easier to go ahead and do all the algebra first and then plug in the numbers. That way you're assured that you have everything set up properly and you're not confusing one number for another. So we're trying to find PO2, but we have everything else. So you're going to start by multiplying both sides by the partial pressure of NO squared. Take this in baby steps. Kp NO, actually edit. So in solving for the algebraic equation, we're going to just take some baby steps. I'm going to multiply both sides by the partial pressure of oxygen. So we end up with Kp partial of oxygen is equal to the partial of NO2 squared over the partial pressure of NO squared. Okay? Now we have Kp, we need to isolate PO2, so we're just going to divide both sides by Kp. We end up with the partial of oxygen is equal to the partial of NO2 squared over the partial of NO squared times Kp. And that's algebraically correct, and we've solved it. We just need to plug in the numbers now. Using the numbers given to us in the problem, we end up getting 0.643 squared over 0.857 squared times 1.50. Okay, and then just plugging that into a calculator, we get 0.375. Now, this takes a little bit of common sense to think about. Because Kp is a unitless number, we need to think about what the actual units of pressure are, because whatever we ended up using for the units of pressure for the entries that we had values for, it will spit back out the same unit for the partial pressure. In this case, it's atmospheres. So if you had mixed units, let's say, and your professor ended up giving you one of them in millimeters of mercury and the other in atmospheres, you would choose one and stick with it. It doesn't matter which one. Just choose one and stick with it. And I have one last problem here for us today. And this one gives us an equation. And it's telling us what temperature it's run out, what our Kc is, and it wants to know what the Kp is. And we have an equation for that. Kp is equal to Kc times RT to the delta N. Now, delta N is the products minus the reactants of the number of moles that are gaseous only, all right? So if I were to have had an aqueous or a liquid or a solid, you would not include it in the delta N. Delta N is only for gases. So in this case, delta N is equal to 1 mole of product minus 1 plus 1. So there's 2 moles of reactant. You have a mole of methane, or I'm sorry, you have a mole of ethane, and you have a mole of water. So this gives us minus 1 as our delta N. For RT, you're going to want to convert T to Kelvin. So in this case, we're going to say T is equal to 330 plus 273, which gives us 603 Kelvin. And you're going to use the gas constant that has liter atmospheres per Kelvin mole. That's generally the one that's used. Given what we have here, we can always use the other gas constant, but we'd have to make some modifications to the equation. So in this case, we're just going to use the 0.08206 liter atmospheres per Kelvin mole. But again, don't worry about the units because in the end, it's going to be unitless. So Kp is equal to 15.0, which is our Kc, times 0.08206 liter atmospheres per Kelvin mole. But again, we're not worried about the units, times 603. We worry about the units for temperature because the conversion is additive. If it was multiplicative, we wouldn't worry about it, but because it's additive, we do worry about it. So make sure you're converting to Kelvin. And then all this is raised to the -1. And if you plug it in exactly like it's seen here into your calculator, then your Kp will end up being 0.303. And that's all there is to it. So key takeaways: products over reactants, only include gas and or aqueous. If you're calculating for delta N, only worry about gases. You're looking at the moles, which if you can't remember how to figure that out, it's simply the coefficient in front of the species. And if there is no coefficient, the coefficient is actually 1. When you're doing this equation that we just did, your R should be the 0.08206 gas constant, and your temperature should be in Kelvin. And that's it. Thank you so much.